On the topic of measuring, one fact will prove challenging is to take a bike hoop and in one fell swoop get it to act like a spring. In this chapter, we will compare diametric compression and tension, take a look at an overview of spring stiffness and natural oscillating frequencies, do an experiment using a bicycle rim as a spring, and then have a brief comment about scientific integrity. This is a graphic that shows diametrical compression of the rim against an immovable base, and you certainly have seen quite a bit of footage of that. If I turn this over and I have the rim attached at the top to a immovable object, then I have diametrical tension. I know that within large limits the rim will behave as a spring, but I want to see if I can demonstrate that so it's visible. This is an admittedly rather crude experiment that I set up, but let's walk you through it. I reinforced the rim a little bit and hung it on these two hooks. Weights will be attached to the bottom of the rim. The block and tackle allows me to raise and lower the weights to a good working level. Within that working level, I can either raise or lower the weights by using this jack. By adding a sufficient amount of weight, I can get the rim to respond elastically by becoming somewhat ovalized like that, and then by putting additional weight on it and removing it, I hope to get the rim to oscillate up and down. I will try to start the oscillation by pushing down on this bar and then lifting it up quickly. If everything goes right, I will see my rim oscillate up and down. High energy experiments require some safety equipment. Let's review a few basics about springs. Here are 4 springs zip tied to a rod. The 2 on the left are weaker springs. The 2 on the right are stronger or stiffer springs, and we're going to hang weights from all 4 of these and see if we can make them oscillate up and down. Here I have the 2 weaker springs with 2 different weights attached of varying amounts, and we'll see what happens when I try to make them oscillate. The heavier weight has a lower frequency of oscillation. Now let's see what happens when we do the same thing with the stronger or stiffer springs. Here I have heavier weights than I had on the left, but in the first instance, the spring is so stiff that the frequency of oscillation is so high you can't even see it. Here are the weights in grams, and going from left to right, comparing the 2 on the left, the 250 gram weight gave us high frequency, small amplitude, and the 500 a smaller frequency but a greater amplitude, and we see the same thing on the 2 on the right. High frequency, small amplitude, lower frequency, greater amplitude. Henry Gavin at Duke ran a few calculations and sent this to me. For a 460 gram rim loaded in diametric tension, the stiffness is about 100 newtons per millimeter or 100,000 newtons per meter. Here is some weight which is causing the rim already to become elliptical, but I'm going to pull down on that weight. But when I let that weight go, here's what I should see. My rim will have a natural oscillating frequency in hertz, and as the weight goes up that is applied to the rim, the frequency will go down. I won't bore you with the calculation, but if you want a nice observable frequency of, say, 2 hertz, I need a whopping 633 kilograms of mass loaded onto the rim. That gives me a force of 6,200 newtons, and Henry Gavin tells me this: the collapse load of a 460 gram aluminum rim is about 7,700 newtons. So to get the natural frequency down to a value that is low enough to count, you need to hang so much mass on the rim that the rim could fail. That's exactly what happened in my first attempt. Here is a place where the rim buckled. You can see a couple close-ups of the buckling, and over here on the side is a crack, and there's the close-up of the crack. Our challenge is actually even greater than that, because what Professor Gavin calculated was really the collapse load of a prismatic hoop, meaning it has a constant cross-section in its entire circle. But what we have with a bicycle hoop is a hoop that is punctuated by many holes in it. So the collapse load is actually considerably less than 7,700 newtons because of all those stress risers where the holes are. So we'll try it again with a different rim, and you'll hear me in the background chatting with Kyle Barris, a friend of mine and a local engineer who does some of these experiments with me. Isn't it? Okay. All right. Now the weight is all on the swing, and we should see quite a huge amount of distortion of it.
Yeah, right? It's elongated for sure.
Yeah. So even though we'll see what happens if I just put a little bit of weight on this thing. If I put too much on it, it'll probably break the rim. That's what happened last time.
There it goes.
Did it spring a little bit?
It did. Absolutely.
Cool. So say that again?
It did, but it did move sideways slightly with sideways deflection.
Oh, you mean it was swinging a little bit?
Yeah, slightly.
That's all right. It's just a crude experiment. And try it again. But there is some vertical.
Oh, absolutely.
All right. Maybe that's all we need to do. You think?
I think we might want to put one more stack of weights
All right.
under the pole.
The more weight is on it, the lower is the frequency.
Yeah.
All right. I think that's good enough.
Okay.
Cool.
I'll support this with this chair.
It would work better if the weights were closer to the rim. Maybe, I don't know. But I think in the videos, we clearly can see the elasticity of the rim.
Mm-hmm.
We can see it acting like a spring.
Absolutely.
So this just, even though it's not a great experiment that shows that you can clearly see that we are putting on additional elongation by pushing down on it, and it has to go back up, and it has to be somewhat springy.
And it does elongate.
Pardon me?
It elongates and then it absolutely oscillates
All right,
vertically.
excellent. That's all we need. I think that's all I wanted to do.
Okay.
We got, not a great shot, but I think it was unrealistic to think that it would be that good. But if we get any kind of an up and down movement, in addition to the side movement, I can focus on that and we'll see it. And if it goes up and down at all, and you said it did, then the only way that can be is because there is a spring. Now it may not be a Hookean spring. That gets even more complicated. So I'll just assume that it is, and assume that we can use the Hooke's law and the formula for a simple harmonic. Oh, the camera's still on, isn't it?
I think so.
Yeah, okay, so the camera is on, and the camera is showing that the rim returned to perfectly
round.
This situation here of getting a very high frequency and very small amplitude that we can't see is exactly what's happening with the bicycle rim. The problem is this: even though my rim is acting like a spring and should display some simple harmonic oscillation, the problem is that the rim is so stiff that in order to get the frequency down low enough that I can see it, the rim will crack first because of the load. This whole discussion was kind of an aside to the main topics of the video, but still interesting, and I'll leave it up to somebody else to try to do this much better than I did with a better apparatus and much better sensing equipment. And one final comment is this: it's always fun when you do an experiment and the results agree exactly with what you thought was going to happen, but sometimes you learn as much when they don't and analyzing why. So as scientists, we never want to fake the results to make them fit with some preconceived notion as to the outcome. So that's what I've been able to do so far. This is not that important, obviously, to this work, but interesting nevertheless. If I'm able to get this to work a little bit better, I'll update this chapter.